Hello students, today let us discuss one more NDT method, that is eddy current method. So this eddy current method is also called as electromagnetic method of testing. So this eddy current method is a non-destructive method. So the main application of this eddy current technique is for detection of surface or subsurface flaws. So it is used for detection of surface or subsurface flaws to detect the conductivity of a component or the conductivity measurement of a component. So conductivity measurement of a component. Then coating thickness measurement. So if a component is coated with some other metal, then the thickness of that coating can be measured with the help of this eddy current technique. So coating thickness measurement. So this technique can be applied, or it is sensitive to material conductivity, permeability and dimension of a component. So this technique is sensitive material conductivity, permeability and dimensions of the product. So when we are using this method for testing, we have to consider material conductivity, permeability of the material and the dimensions of the product or the component. So this method is very sensitive to these three properties of the component. So when you are selecting this method, you have to check for material conductivity of the component, then permeability and the dimension of the component. So the principle of working of this method. So eddy currents can be produced in any electrically conducting materials that is subjected to alternating magnetic field. So eddy currents can be produced in any electrically conducting materials which is subjected to alternating magnetic field. So that magnetic field must have 10 Hz to 10 megahertz of the strength. So eddy currents can be produced in any electrically conducting material which is subjected to alternating magnetic field. So which is 10 Hz to 10 megahertz. So a component is subjected to alternating magnetic field. But how this magnetic field is produced? So alternating magnetic field is generated by passing an alternating current through a coil. So alternating magnetic field is produced by passing alternating current through a coil. So this coil can have many shapes and it can have 10 to 500 turns of wire. So the coil can have many shapes and can have between 10 to 500 turns of wire. So I have told you that this method is sensitive to conductivity, permeability and the geometry of the component. Why it is sensitive? Because the magnitude of the eddy currents generated in the product will depend upon the conductivity, permeability and the shape or geometry or the setup geometry of the product. So the magnitude will depend on the conductivity, permeability and the shape or geometry of the product. So that is why this method is sensitive to these three components of a product. So the magnitude of the eddy currents generated in the product depends on conductivity, permeability and setup geometry. So any change in the material or the geometry can be detected by the excitation coil as a change in the coil impedance. So if there is any change in the material or the geometry, so if this is the component, if there is a hole here, so the geometry of the material is not same throughout, so there is a change in its geometry. So if there is change in the geometry, then the excitation coil will cause change in coil impedance. So by this change in the impedance, we can detect the change in the geometry of the material. So the most simple type of coil will comprise a rod with several turns of wire wound at one end and which is positioned close to the surface of the product to be tested. So here we can see that this is a rod, that is ferrite rod. So this is a ferrite rod and there is a wire wound on it. So this is the wire with number of turns. So this wire or this rod is placed close to the surface of the product to be tested. So if this is the product to be tested, this rod is placed close to this surface. So here you can see that there is no crack and this pattern of the eddy currents is circular pattern. Several turns of wire wound at one end and which is placed close to the surface of the product to be tested. So here if there is a crack which is occurring in the component or in the product surface, then the eddy current must travel further around the crack and it is detected by the impedance change. Here there is a surface crack and this pattern is not circular but it has a distorted circle and the currents go round and under the crack. So there will be increase in the impedance in this case. So if there is a crack, this pattern will not be circular, it will have distorted circle and the change in the impedance will be seen. That is, here impedance will increase. So this is the example for testing the surface cracks. When a crack occurs in the product surface, the eddy current must travel further around the crack and is detected by the impedance change. So this is a coil with a single winding. So here there is single winding. So coils can be used in pairs also. So generally called as a driven pair, and this arrangement can be used with the coils which are connected differentially. So in this way, so here we can see there is coil with two windings known as a driver pair of or differential probe. So coils can be used in pairs called as driven pair or driver pair or differential probe. So this method or this arrangement can be used with coils connected differentially. So in this way, lift off, that is the distance of the probe from the surface, that is signals, can be enhanced. Lift off signal is nothing but distance of the probe from the surface. So you can enhance the signals by this differential arrangement. So coil windings are in a bridge. So here you can see this is a bridge formed between these two coils. So coil windings are in a bridge. The scan across the crack so that each winding sees the crack in turn. So this winding has, if there is a crack in between these two probes or these two rods, these are nothing but ferrite rods which are differentially connected to each other, and there is a bridge formed in between. So if there is a crack here, then this crack will be scanned by both the windings. So scan across the crack so that each winding sees the crack in turn. Okay, and this lift off, which is nothing but the distance of the probe from the surface. So this lift off, which occurs simultaneously, get cancelled out. So lift off signals which occur simultaneously and are cancelled out. So here the coils can also be used in a transformer type configuration where one coil winding is a primary one and the other, that is it may be one or two coils which are used as the secondary one. So this coils can also be used as a transformer type configuration. So coils can also be used in a transformer type configuration. So transformer configuration means it has one primary coil or primary coil winding, and the other, which is the secondary winding, it may have one or two coil windings. So where one coil winding is a primary and the other, which are one or two coil winding, are used for the secondaries. So here this is the primary coil, which is in the blue color, and this coil is wound over the secondary coils. So here this primary coil is for excitation purpose. So here there are two secondary coils which are named as S1 and S2, which are both in orange color, and these two coils are connected differentially as I have shown in the previous figure. So the product which we are testing moves through this coil or through this setup. So there are totally 3 windings in this transformer type coil. Now the detected eddy current signals, which contain the amplitude and phase information, can be displayed on the CRT type displays, or it can also be displayed on the non-digital display. So CRT is nothing but the cathode ray tube displays, or you can use any non-digital displays also. So the detected eddy current signals, which contain amplitude and phase information, can be displayed on CRT type display or non-digital displays. So the signals may be displayed as the actual or the absolute signal which we have received, or with the appropriate electronics only a signal change is displayed. So signal can be displayed as absolute signal or appropriate electronics only a signal change is displayed. So the best results from this testing is obtained only where only one product parameter is changing, that is presence of a crack. So if there is only one type of problem in the product, that is if there are any cracks present, such type of parameters, such type of change in parameters are best displayed with the help of this eddy current method. So one parameter change, that is example here is presence of a crack. So in practice, changes in eddy current signals are caused by difference in composition, hardness, texture, shape, conductivity, permeability, and geometry. So the eddy current signals are changing because of change in or difference in the composition, hardness of the material, texture of the component, shape of the component is changing, conductivity is changing, or permeability or geometry is changing. So when these eddy currents change, then we can check it or we can detect it with the change in the impedance. So change in eddy current signals are caused by difference in composition, hardness, texture, shape, conductivity, permeability, and geometry. So, in some cases, the effects of the crack can be hidden by changes in other parameters. So, there may be a crack in the material and there may be no change in the composition, hardness, texture, shape, conductivity, permeability, or geometry of the component. In such cases, when you use this eddy current method, it may not show the crack or it may not show any change in the eddy current. So, we may simply accept the component or we may simply reject the component thinking that there is no crack in the material. So these changes will not occur and we may think that there is no crack in the material and we may accept the component. So we have to select the coils for the configuration, size, test frequency so that we can enhance the detection of the cracks, the conductivity, and the metal loss as we require. So the depth to which this eddy current penetrate a material can be changed by adjusting the test frequency. So depth of eddy current penetration in a material can be changed by adjusting the test frequency. So if you increase the frequency, the penetration will be less. So higher the frequency, lower the penetration. But if you increase the frequency, the sensitivity to detect small defects will become less. So higher frequency will cause low sensitivity to small defects. So if you increase the frequency, then small defects cannot be detected. And larger coils are less sensitive to surface roughness. So we have to consider so many parameters here, like the frequency, the size of the coils is also very important. If you are choosing larger coils, then it will ignore the surface roughness, are less sensitive to surface roughness. So smaller coils are more sensitive to surface roughness. So we have a electronic unit which are able to operate a wide range of coil configuration in absolute or differential modes and at wide range of frequencies. So there is a new or the latest electronic unit can be used to operate wide range of coils, coil configuration in absolute or differential modes, that is single or double coils, and the size of the coils can be varied, and at wide range of frequencies. So for surface testing of cracks in single or complex shaped components, coils with a single ferret core winding are normally used for. So if you want to test a surface of a component, so if the shape of the component is complex or it is single also, if you want to test the cracks in it, then coil with a single ferret cord wire, which I have shown in the first figure. So here, so this is the first figure. So this setup is used to check surface cracks in a single or a complex shaped component. So the probe is placed on a component and it is balanced with the help of electronic unit controls. So the probe is placed on the component which we are measuring, or which we want to detect for cracks, and is balanced. The probe is balanced by electronic unit controls. So as the probe is scanned or moved across the surface of the component, the cracks can be detected. So as the probe is scanned across the surface of the component, the cracks can be detected. So here in the first figure, we have to maintain the lift-off distance accurately. The lift-off distance, so that is nothing but the distance between the probe and the surface of the component which we are testing, must be accurately maintained for accurate results. So the second type, that is the differential coil configuration, is used with higher speed scanning systems. So this is about the first type of winding, which has only one rod, that is the ferret rod, to which the coil is wound and it is brought nearer to the surface of the component which we are testing. The second type, that is the differential coil, which we have already seen. It has two rods and they are connected differentially. So the differential coil configuration is used with high speed or with higher speed scanning systems, where the lift-off effect and the vibration effect can be cancelled out to an acceptable extent. So here there is a electronic component which is used for the testing, and it has also got controls in it. So it is the illustration of eddy current testing of drawn tube for longitudinal defects. So most eddy current electronics have a phase display, and this gives an operator the ability to identify the defect condition. So like this component, the electronic eddy current electronic units will have a phase display on it. So this will help the operator to identify the defect conditions. So here the signals from the cracks, liftoff and other parameters can be clearly identified. So we will get signals from cracks, liftoff and other parameters can be easily identified. So eddy current test is purely electrical. So the coil unit need not contact the product surface and this technique can be easily automated. So the coil units need not contact the product surface and so it can be easily automated. So now what are the advantages of eddy current testing? So this method is suitable for determination of wide range of conditions of conducting material such as defect detection, composition, hardness, conductivity, permeability, and also in a wide variety of engineering metals. So it is suitable for, so not only for the detection of defects but also other parameters of a component like the composition, hardness, conductivity, permeability can also be tested with the help of this method. So information can be provided in simple terms. Often it may be go or no go. Then phase display, that is the electronic units can be used to obtain much greater product information. So information is provided in a simple manner. Often go or no go. So extremely compact and portable units are available. So here non-consumables except the probes which can be sometimes repaired. So all the components which we are using here are non-consumables except the probes which can be repaired now and then. So there is flexibility in selection of the probes and wide and the test frequencies to suit different applications. So we can change the probes according to our requirements as well as the test frequencies can also be changed. So there is flexibility in selection of probes and test frequencies to suit different applications. And this method is suitable for total automation. So it can be totally automated. So now what are the disadvantages of this method? So the wide range of parameters which affect the eddy current responses means that the signal from a desired material character, that is the crack, can be masked by an unwanted parameter. For example, the hardness change. That is why careful selection of the probe and the electronic will be needed in some applications. So wide range of parameters which affect the eddy current responses means that the signal from a desired material characteristic, example, a crack, can be masked by an unwanted parameter. Example, hardness. So this crack may be closed or may be masked by the hardness of the component. So that is why we will need to select the probe very carefully, and the electronics which we are using also must be selected very carefully. So careful selection of probe and electronics will be needed in some applications. So generally this test is restricted to surface breaking conditions and slightly subsurface flaws. So the deeper flaws which are present inside the component cannot be detected with the help of this method. Tests are restricted to surface breaking conditions and slightly subsurface flaws. So this is all about the eddy current or electromagnetic non-destructive testing method. I hope you have understood the topic. Thank you.